Precision in measurement is important in everyday life. Let's say you go to the Getaway with a friend. If the bartender sells you a pint of soda, but measures inaccurately and gives you only half a pint, you might be a little upset at having to pay full price. In the same way, accuracy is important in science, since it tells a scientist how precisely they have confirmed a value in nature or verified a quantity predicted from theory. There are different types of errors in a measurement: resolution error, random error, and systematic error. Resolution errors come from limited precision in a measuring device, like the inaccurate cups at the Getaway. If you try to measure exactly 1 pint in a cup that is only accurate to half a pint, all you can guarantee is that you measured more than half a pint and less than 1 1/2 pints. Random errors can be seen in any set of multiple measurements. For example, if 5 people ask for a pint of soda, there might be a little more in some glasses and a little less in others. Finally, systematic errors cause all data points to be skewed in the same direction. This can happen when the measuring device is calibrated incorrectly. If someone moved the 1 pint mark higher on our measuring glass, then every customer would get more than 1 pint. Typically in lab, you will address systematic errors qualitatively rather than finding a numerical value for them. Still, you must find and record numerical values for the resolution and random errors. The resolution error can be found immediately when you take your measurement. It is typically the smallest increment on your measuring device. On a meter stick, that is 1 millimeter. On a device with a digital interface, like a scale, the resolution error is usually 1 in the last given digit. The random error in a quantity can only be found if you measure it multiple times. The random error is given by the standard error and applies to the average of the measurements, not each individual measurement. To find the average, add the measured values, and then divide by the total number of measurements taken. Next, find the standard deviation. The standard deviation is a way of saying, if I measure a value over and over again, how far should I expect any given measurement to be from the average? To find this, we should take into account how far away from the average each value is, and then divide by the total number of measurements taken minus 1. Finally, take the square root of the whole thing so that the standard deviation has the same units as the average. The standard error is simply the standard deviation divided by the square root of the total number of measurements. That means that the more you measure a quantity, the more accurate the average value is. Now you have 3 types of error: the resolution error, the random error, and the systematic error. Typically, you won't have a numerical value for systematic error, but you will need to combine the resolution and random errors to find a total error. If a gang of physics thugs stops you in the Getaway and asks you how to combine these errors, what would you say? You may think to just add these errors, but that is an overestimate since sometimes the errors cancel out. Instead, we combine these errors in quadrature. Think of these errors as sides of a triangle, where the x side is the resolution error, the y side is the random error, and the hypotenuse is the total error. The formula for the total error is the same as the formula for the hypotenuse of a triangle. This method can even be generalized for 3 or more errors. In lab, once you measure a value, you probably want to calculate a new value from your measurements. For example, You may measure the diameter and height of a cylinder and calculate the volume from these measurements. If there is an uncertainty in diameter, then there will be a corresponding uncertainty in volume. Similarly, there will be another uncertainty in volume due to the uncertainty in height. There is a useful general formula for this. If z is a function of x and y, then the uncertainty in z due to delta x is the derivative of z with respect to x times delta x. In the same way, the uncertainty in z due to delta y is dz dy times delta y. Therefore, if we add in quadrature, we find that the total fractional error in z squared is equal to dz dx times delta x squared plus dz dy times delta y squared. This may look complicated, but it simplifies nicely for common formulas of z. If z equals x to the a times y to the b, then the formula for fractional error in z is delta z over z squared equals a times delta x over x squared plus b times delta y over y squared. Going back to our example, if the volume of a cylinder is pi over 4 times d squared times h, the formula for total error in volume is delta v over v squared equals 2 times delta d over d squared plus delta h over h squared. Let's try an example. Follow along with the calculation and feel free to pause the video if you need time to work. If I have a cylinder with diameter d equals 1.9 plus or minus 0.1 centimeters and a height h equals 3.78 plus or minus 0.02 centimeters, what is the total error in volume of the cylinder? From the diameter and height, the volume can be calculated to be 10.717 centimeters cubed. Remember that we already found an equation for the total error in volume. Solving the formula for delta V and plugging in numerical values, we get the error in volume to be 1.1 centimeters cubed. We then record the volume as 10.7 plus or minus 1.1 centimeters cubed. In summary, remember that to find the total numerical uncertainty in a measured quantity, add the resolution and random errors in quadrature. The resolution error is obtained from the measuring device, and the random error is the standard error of multiple measurements. When you calculate another value from measured quantities, you must also propagate the error. With these rules in mind, you'll be well prepared for your physics labs and for trips to the getaway.